Today I'll be continuing my talk on reliable data transfer protocols, and more specifically, in the previous video, we discussed how we can use pipelining to better improve the utilization of our sender program. So sender program previously send and wait, where we sent a packet and then we waited for the packet. But then we discovered that if we do pipelining, we can get a almost linear time better usage of our sender. Instead of just spending all that time idling, so we can send more packets over the network and pipeline them. But then we realized that afterwards, in order to implement our mechanism up here for having our sequences, we noticed that we needed to effectively have these notions of corrupted ACKs and NACKs. So in order to have the corrupted NACKs and ACKs, coverage for assuming that a NACK or NACK is not corrupted, we need to have these states, 0 and 1. And because we have alternating states, we can't possibly use pipelining anymore. So because of that, I'm going to show you how to implement two different protocols. One of them is called go backend, and then the other one is going to be called selective-repeat. So let's start with the very first one, which is go backend. So go backend, essentially what it is you're going to have a window of packets. Okay, so we're going to have some large window of packets. And notice from the name that we have n in the name as well. So that will give us some sort of hint in terms of like what n means. So what n means is that we're going to have a series of numbers inside of here. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and so on. Let's say our n is 3. Just at the beginning. Here. So we're going to have an n of 3 over here. N equals 3. Effectively what go back n does is that we're going to have a timer. Just like our previous implementation, we're going to have a timer. And then what we do is we're actually going to send all 3 packets over to our sender, to our receiver. So our receiver will store as a variable this very important thing called a cumulative ACK. And what that means is that this thing will actually store the cumulative value, so the lowest value that it expects so far, and then it will actually return that every single time. So what I mean by that is, okay, we have this window with go back n, which is size 3. What we're going to do is we're actually going to send all 3 packets over to our receiver. So we have our receiver over here, and we have our sender over here. The sender will send packets over to the receiver. It will actually send n packets all at once. Then the receiver will say, okay, I'm actually going to have a cumulative ACK of 0 over here. Meaning 0 is what I'm actually going to be expecting to receive. That is the next packet that I don't have yet, that I'm expecting to receive. If I receive something else, I will tell it what the next largest packet is that I received, if that makes sense. So let me go through this logic carefully, and then it'll actually make more sense once it becomes clear what actually happened. So the cumulative ACK right now is default initialized to -1. What's going to happen is the sender will send over packet 0. We'll send over packet 0. We'll send over packet 1. We'll send over packet 2. Now my receiver says, okay, so far I have up till -1. I'm expecting to receive packet 0, which is the next packet in my sequence, as my sequence numbers goes up. If I receive packet 0, I'm going to send it back to the sender that, hey, yes, I received packet 0. So effectively what I do is I'm going to have this array over here, again, and then I have this window. So the very first thing I do is I'm going to send packet 0, 1, 2 over the network. My receiver will receive packet 0. It will see that the cumulative ACK is a -1. And I'll say, okay, -1 plus 1 is 0. I'm expecting to receive 0. I receive 0, so I'm going to go over and send an ACK back to my sender. The moment my sender receives an ACK of 0, this means that yes, I'm done with 0. I can actually move my window forward 1. So then what I do is I take my window here and I move it forward a little bit. Right? So now that I move my window forward a little bit, I'll be able to, because I already know that that one got sent, I can send the next one in order. I can't copy. Oh my gosh. Okay. I know that that one got sent, and then I can continue on with the next one. So the next one would be 1, 2, 3. And similarly, once I get my ACK back, then this number over here gets incremented. So then I have a 0. So I received all numbers up to and including 0. But then I'm expecting to receive a 1. And then I receive a 1. And in the case that I receive a 1, then I'm going to send back an ACK saying 1. And then my sender will say, oh, I received a 1. Let me just move forward this window over here. So I'm going to send over this window and then move it forward. Move it forward so that you receive the 1. Like that. Okay? After I receive the 1, we're going to move the window forward. But this is the best case scenario. The best case scenario is when you're sending all of your packets and then you receive them precisely in the same order. But in reality, that's not going to happen. You're going to have packet loss because, as we said, it's an unreliable network. So essentially what we need to do now is what happens if we are, in this case where we send our next packet, sorry, this is n equals 3, it should be less. Sorry, I just realized this should be pointing here. N equals 3, so we have our packet here, and then we're at some stage in sending our packets. Let's say that we actually send them in a different order. What actually happens? Okay. So let's take our example here. Whoops. Copy, paste that. So let's say we're currently at the stage where we're here. So n equals 3, we're on packet 3. What would be the sequence number that we expected here? So this means that we've already sent 3, which means that this guy is over at 2 and he's expecting to receive 3. But let's say our packet 3 gets sent over. Packet 3 gets sent, but then it gets lost as part of transmission. So something happens, but we also send packet 4, and we recently also sent packet 5. Okay. Now packet 3 gets lost in the process because of some network transmission. Let's say packet 4 also, but we get packet 5. But then in our receiver, we said, oh, but wait a second. My cumulative ACK is only 2. Why did I receive a 5? I'm expecting to receive a 3. So what this is actually going to do is actually going to send back its cumulative sum, which is 2. And then the sender will say, I received a 2. Clearly it means that it only received up till this point. Up till this point. It didn't receive anything since then. I'm actually going to resend all of those packets. And I'm actually going to not resend them, but I'm going to ignore the duplicate ACKs that I received back because it's meaningless for me. I'm not interested in that. My window doesn't actually change. But instead what we're going to have, and then you might be asking, when am I ever going to resend those packets? We're going to have a timer. And this timer will run again, and then this timer will resend all of the packets, which is why it's called go back n. It's called go back n because we're sending go back all n packets. So the moment you have the timer interrupt, it sends back all packets. So then you might ask, okay, how does this timer work? Does it work for each individual item within our window of size n, or does it work so that there's only like the oldest unACK packet? And the answer is the oldest unACK packet has a timer. The moment you receive a cumulative ACK that includes that position within the window, then you choose to start a new timer. So in this case, we would actually get the 5, we would send an ACK back here. We had an ACK back with 2, which was bad. Some time expired, then the timer expired, and afterwards it said, oh, okay, well, we're just going to resend all of them again. 3, 4, 5. And now that our 3, 4, 5 sent, then we're sending back the appropriate acts back to. So here we were sending 3, here we were sending 4, and here we were sending 5, and the window progresses. But the moment you receive the 3, what happens? Well, the 3 happens, then we're going to start a new timer for the 4. And the reason you start the new timer for the 4 is that it's an unact packet. So anytime you receive an act that advances your base pointer forward, you start a new timer and you deactivate the old one. So this way, in some sense, we guarantee that from receiving an ACK, it will take at most time t, where t is the amount of time it takes for the timer to time out in order to send the next packet, if that makes sense. So timer t. Okay. So just because we receive an acknowledgement containing a duplicate ACK number doesn't mean that we're going to be resending the value. We only resend it the moment we get a timeout. So that's the critical observation of the go backend protocol. And also that we send it back for the entire sender window. So yeah, I hope this makes sense. Now another complication to this is that sometimes we actually use sequence numbers. So we might have an array, but we might actually have modulos. And that complicates it a little bit because when you're expecting the sequence number, it can get a little bit complicated in terms of how you're repositioning it in your sender array. So what I mean by that is we have this large array with 11 items, but if our sequence numbers only go up to 3, we're actually going to have to do modulo 3. So we're going to have 0, 1, 2, 0, 1, 2, 0, 1, 2, 0, 1, 2. And then we're going to have a base pointer that will point to the base of our window. And then we're going to have another pointer that points to the end of our window. Now when we receive a sequence number, we're only going to be receiving, let's say, 0, 1, or 2. You need to be careful if you're sending this data through, let's say you have a Python list or you have a Java array, and you want to be able to send the data over, you're going to want to map the sequence number back to an index. And I'm just going to point out that it can be a little bit tricky. There's some edge cases to consider. I won't go into the details. You can comment below if you're actually implementing this in Python, Java, or whatever programming languages, because of actually getting the right indexing right. But it does take a little bit of tricky cases to consider when you're using sequence numbers. For this example, I didn't use sequence numbers. I just assumed that there's an unbounded number of sequences. So yeah, I mentioned that there's go backend, but then there's also another one called selective repeat. So what is selective repeat? Selective repeat is, again, we see that there's a repeat, so it's similar to the automatic repeated request protocol. So we have the repeat in here, but then we have the word selective. So what selective means is that the receiver individually acknowledges all correctly received packets, but the sender only resends packets for which ACK was not received. So again, we have n consecutive sequences inside our sender window, but this limits the number of sequences sent only for the unacked packets. So what this means is, let's create our array again. So we have our array here, and we have our array of numbers, labeled 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And again, we're going to have a window, let's say, of size 3. And just for concreteness, I'm going to start off here. And we're going to have a window of size 3. It's labeled over here, that. Alright, so now we have a window of size 3, and we're using selective repeat. Now, selective repeat also has a cumulative sum on the other end. But what we do for the receiver is that we also store a buffer. So for the buffer is we're actually going to buffer the value if it's out of order, and then we get to keep it. And then only if it times out for that specific packet we resend it, but we don't need to resend the original one as well. So effectively what happens is we're going to be sending packets 4, 5, 6 as we're moving forward in it, but then we're going to have several more states in terms of these packets that we're sending. We're going to be having one state where it is unsent, unact. We can have a sent packet act, or we can have a sent packet unact. So obviously if it's unsent, it's unact. So typically we get in that case where we advance the forward pointer over here. When we advance this pointer over to the next one, we're eventually going to get to 7, and 7 is not going to be sent, and it's neither going to be act, obviously, because we haven't sent it. The other case is where we sent something, but it's unact. In go back n, typically when we receive these, we receive the cumulative act. So it's cumulative in the sense that like this is what we received so far. So the cumulative acknowledgement means that for all the values before, they were act. So we never ever had the case where we act something. Let's say the 5 was act, but not the 4. Now this is different. In selective repeat, we're very selective about what we're sending. We're sending each individual item within the array. So instead, we can selectively send 5, buffer it within our receiver, but then actually we won't mark it in the other one. So we're going to act each one individually. So we have our receiver over here. The receiver will actually act it as well, which is really, really neat. So we have this, like this, this, like this. So the receiver will act it. Now, what the nice thing is that we're going to be sending the 4, 5, 6. Imagine the 4 gets dropped when it goes over the network. Then we have the 5 and the 6. Now the 5 gets act back, and so does the 6, which is nice. But then the 4 packet gets lost when it gets sent back. Now the 4 packet will need to be resent, so we're going to have an individual timer for the 4 packet. And the 4 timer will get sent back. The moment you have a contiguous sequence of act sent packets in the prefix of the array, so at the beginning of the array, then we will be able to move the window forward and try sending more packets. So at any moment inside our sender window, the sender window will be equal to whatever sequences bottlenecked by the leftmost packet sequence number not being act. So in this case, the 4. The moment the 4 gets act as well, then we can move it over 3. Now let's consider another case where only the 5 got act, but the 4 nor the 6 got unact. Well, the 4 timer likely had to have started before the 6 timer, so the 4 timer will go off, but it won't send 5 and 6 as well. It'll only send a packet for 4. Now it'll send a packet for 4 over to the receiver, and then we send that packet for 4 over to the receiver, and then we're going to send a packet over for 6 also. Later though. You send the packet for 4. After some time t, later we're also going to send the packet for 6. Okay? After we send the packet for 6, then we're basically done. Because then it's going to send to the receiver, and hopefully the next time it won't fall out over the network. So effectively now we have individual timers for each one. We don't just have one timer for the entire thing. But now we have one potential edge case, which is very interesting. So recall that I mentioned sometimes sequence numbers are limited. It's not unbounded. So we have an interesting case where we could actually have some conflicts. Consider the following case for a selective repeat. We can have a case where we have a window of size 7. So 1, 2, 3, 4, 5, 6, 7. Like this. And then our window size is n equals 3. Okay. So what we're going to have is we're going to have 0, 1, 2, 3, 0, 1, 2. Sorry, the window size is 4. So I have a window size of 4, and then we have this network over here, and then we have our sender over here, call it this box, and then another over here. Okay, so effectively we're going to have an array, and then we're going to send the packets over here. The very first thing is we're going to send packet 0 over. So then internally inside of here, we're also going to have an array of 7. Oops. Very first thing is we're going to send over packet 1, packet 0. This doesn't get lost over the network, but then our response times out. Fails here. Afterwards, we're going to send packet 1, but then our reply times out. Then we're going to send packet 2, then our response times out. Then we're going to send packet 3, but then our response times out. Then we're going to send packet 0 again. But what happens is, essentially, on the right side, we were receiving these packets, right? But we were actually advancing the pointers forward. We were having the illusion that we received packet 0, we received packet 0 and 1, we received packet 0 and 2, we received packet 0 and 3. And now, what happens is, over here, we said, oh, we never received anything. Timer for this one, timer for this one, timer for this one, timer for this one. We resend the same packet 0 here, that corresponds to this, but inside of here, when we receive this packet 0, we're correlating it with this. So how do we actually guarantee this problem? This problem where we have this sliding window, right? The sliding window moves over to the right, but actually it's causing a problem because we want to be able to not have this happening. So how do we prevent this from happening where we have this sliding window, but then here we're actually thinking that this one is actually a duplicate packet for this one. So we're actually, if we're sending messages over, we'd be having the same message twice because the left side is unaware of the right side. And a simple way to prevent this from happening is that we need to see what is the relationship between the sequence number size and the window size to avoid the problem. So if we take an observation, what actually happened was that we looked through the window and then the window size got too large and then it wrapped around. The window size is slightly more than half the size of the total sequence number of the sequence numbers. But if the sequence numbers only went up to 0 and 1, would this have happened? We would have gotten 0, 1 with the window size of 2, which is half the size. So 0 and a 1. And then we would have expected a 2, but then we never would have gotten the ACT for the 2. Similarly, we never would have gotten the ACT for the 3 because the 0 would never have gotten confirmed. I think the moral of the story here is that the window sizes should be smaller than the number of sequences, because the moment you have one as large as the number of sequences, then you run into this issue where it could possibly wrap around and then you have duplicate ACTs being sent. So yeah, actually the answer to this, if you spend some time looking, is it has to be half the size. So the window has to be half the size of the sequences. So make n equals half the size and then it will work. So yeah, this is selective repeat. So what are the advantages and disadvantages of both approaches? Well, go back. Selective repeat is nice in the sense that selective repeat, you don't need to resend something if it already got acknowledged. But the disadvantage is that you need to maintain a buffer on the receiver's end. In go back end, you don't need to have the buffer, but then you're resending packets maybe unnecessarily because you're really only expecting one at a time. So yeah, those are the advantages and disadvantages of the two approaches. If you look at the implementation of TCP, TCP implements a little bit of a hybrid. It's a little bit of a hybrid in the sense that in TCP, the implementation actually doesn't mention if you need to buffer the TCP packets as you receive them. But in the TCP recommended implementation, and what most people use, is that they'll actually buffer the sequences. And that's the whole idea of the fast retransmission, where you only send an ACK, but you only resend if you receive an ACK 3 times. So yeah, I hope you guys enjoyed this video and I hope it makes sense. And thanks for watching. If you have any questions, please leave them down below.